This is a display powered by vacuum. It uses 3D printed microfluidic logic circuits. Let me take you on a journey from a single pixel to a fully multiplexed matrix. Last time we built logic circuits powered by air. We made resistors and transistors that use vacuum instead of electricity and connected them into a ring oscillator, a circuit that produces rhythmic signals. Those signals control a few small soft muscles, almost like a simple nervous system. And together they even started to walk. After that video, I got a lot of great comments. Ideas ranging from soft creatures to vacuum-powered CPUs. But my mind kept coming back to one idea. Could we use that vacuum logic to build a display? Let's start with a single pixel. First, we print the pixel body and hammer in a blunt needle to access the internal channel. Then we cast the membrane from soft silicone. I like how shiny it is. This is our first pixel. In the off state, the membrane sits flat. To turn it on, we use this vacuum pump. Connect them together and vacuum pulls the membrane down. This is our on state. Instead of manually connecting and disconnecting, we can use a solenoid valve. Pressing this button switches the output between atmospheric pressure and vacuum. But a display is more than one pixel. What if you want 4, 9, 16 or more? Controlling each pixel individually would require a lot of solenoid valves. There has to be a better way, and there is. It's called multiplexing. Imagine a grid of rows and columns running behind the pixels. By activating one row and one column, we can select a single pixel. Repeat this many times and we can draw an image. Now here's the key part. We only need solenoid valves for the rows and the columns. So instead of 16 valves, we only need 8. But while multiplexing reduces the number of solenoids, it creates a new problem. How do we make sure a pixel turns on when its row and its column are active? We need a logic circuit that activates the pixel when both its inputs, the row and column, are active. What we need is an AND gate. Let's define two logic levels. Atmospheric pressure is 0, vacuum is 1. For the AND gate, as long as at least one of the inputs is 0, the output will also be 0. Only when both inputs are 1 does the output turn to 1 and the pixel becomes active. Luckily, building an AND gate with our vacuum logic is quite simple. We just have to combine two vacuum transistors in series. But how does a vacuum transistor actually work? At its core, it's a tiny valve. It behaves a lot like a P-channel MOSFET, just using vacuum instead of electricity. For simplicity, I'll just call it vacuum transistor. It's built from 3 layers: a flow layer, a membrane and a control layer. The flow layer contains 2 channels separated by a wall, but open towards the membrane. When vacuum is applied, the membrane is pulled in and seals the channel. The control layer has one large opening. Applying vacuum there pulls the membrane even further. Stack everything together. With atmospheric pressure at the control input, vacuum in the flow channel pulls the membrane only tighter. Switch the control to vacuum and the membrane pulls down, connecting the channels. Now vacuum can flow across. Let's integrate the AND gate into the pixel. It now consists of 4 layers: the control layer, the logic membrane, the flow layer and the pixel membrane. It's easier to look at the negative space of the channels and hide the pixel cavity for now. Vacuum enters from one side. To reach the pixel, it has to pass 2 vacuum transistors. Together, they form the AND gate. The row input opens the first transistor. The column input opens the second. Only when both are active does vacuum reach the pixel, pulling the pixel membrane in. Let's print it. One key detail: the parts are printed with the sides clamping the membrane facing towards the smooth build plate. That gives us a flat interface and a good seal with the membrane. First, we deburr the edges. Look at those tiny channels on the inside. And once again, we hammer in the blunt needles. For the logic membrane, we cast a thin silicone film. Cut it using a mask and punch a central hole. Now we can assemble the full stack. A single central screw holds everything together. You can actually see the membrane change color as it's pressed against the print. Clamping pressure turns out to be crucial. For small parts it's less of an issue, but on the ring oscillator I had to use these external clamps. That's why this pixel is designed around one central screw. It lets us precisely adjust the pressure on the logic membrane. Lastly, we add the pixel membrane. This is our finished pixel with logic built in. To test it, we connect the vacuum supply along with the row and column inputs. Two solenoid valves control the row and the column. Activating either one alone does nothing, but activate both at once and the pixel pulls in. There's just one issue. Once the pixel is pulled down, it latches. The only way to release it is by lifting the pixel membrane. Let's fix it. Here's a plan. The same architecture, but now we have 4 pixels. Each pixel still has a vacuum supply, followed by an AND gate connected to the pixel. New is this third transistor, the release. This one is connected to the atmosphere. By pulsing a row and a column, we can activate a pixel. Because the pixel is latching, it stays on, even after the pulse ends. We can activate a second pixel in the same way, and build up a pattern 1 pixel at a time. To release them, all release transistors are tied together into what I call global release. When this global release is activated, all pixels are vented to the atmosphere and return to their initial state. Printing took 18 hours. But here it is. There are 12 vacuum transistors in these parts now. This is starting to get complex. I've gotten a lot of comments asking about my transparent prints. And if you've ever tried printing with transparent filament, you might have been surprised that parts come out with this whitish milky look. Well, I certainly was. But it actually makes a lot of sense. When printing with filament, parts aren't truly solid. Even at 100% infill, tiny gaps form between the extruded strands of plastic. Light bends as it passes between different materials, so when it hits a part full of these tiny gaps, it scatters, making the part appear white instead of transparent. With the right settings though, using 100% infill, slower print speeds, aligned rectilinear infill and slight over extrusion at higher temperatures, you get fewer gaps. Parts that are much more transparent and, most importantly, much more airtight. Back to the pixel matrix. As always, we hammer in the blunt needles and prepare the logic membrane. Now we can stack the layers and screw them together. Next, we cast the pixel membrane. I added these channels to make sure the atmosphere ports of each pixel won't get blocked. Let's add it to the stack. And here is our first pixel array. To bring the display to life, I put together this electro-pneumatic controller. It's connected to a powerful vacuum pump. An Arduino controls multiple solenoid valves, each capable of switching between atmosphere and vacuum. We connect the rows, columns and release. I programmed a simple pattern that turns the pixels on one by one. It didn't work right away. I had to fine-tune the pressure for each pixel until it finally worked. Now we can try different patterns. This one I call the wandering pixel, or turning on entire rows. and even all at once. I love how the edges wiggle. The pixels hold their state without any energy input, almost like memory. And we can also release them manually by pulling a syringe. Holding the matrix against the light reveals an interesting effect. But is this really efficient? Right now, it takes 5 solenoid valves to control just 4 pixels. So let's grow more. Here it is, essentially the same as before, just larger. Now we're really getting somewhere. This is probably the most complex microfluidic design I've ever created. Once again, we print the parts. Each one took almost 2 days to print. First, the flow layer with all the pixels. It came out beautifully. There's something mesmerizing about complexity and scale. Honestly, it's surreal what consumer 3D printers can achieve these days. We add a blunt needle for the vacuum supply. Now onto the control layer. You can see all the row and column channels and the openings for the transistors. Once again, we hammer in the blunt needles. For casting the logic membrane, I printed this frame and glued it to a sheet of glass. Then poured silicone, cut it, and punched the holes. Now we can stack the layers and screw them together. This time I added some UV glue to the inputs to ensure they are airtight. Lastly, we cast the pixel membrane, demold it, and add it to the stack. With everything assembled, we can connect the vacuum supply and all the control inputs. When I powered it on for the first time, some pixels activated, others didn't respond at all. I kept running the same program, toggling through all pixels, while trying to fine-tune the pressure. Eventually I got something that works. Let's see what this thing is capable of. I came up with a whole range of patterns, starting with simple ones, activating pixels one at a time. This one I call zigzag. Then there's a diagonal wipe, the spiral, and the checkerboard. It's also possible to activate entire areas at once. This one I call the growing corner. When trying to activate all pixels at once, you can see that the columns closest to the vacuum supply turn on first. My guess is that we are starting to hit the limit of the supply channels. They probably need to be a bit larger. Of course, I had to try displaying numbers. Some work better than others on a 4x4 matrix. And letters. More pixels would definitely help here. I also tried a few smiley faces. Happy, laughing, sad, and angry. Finally, I wanted to see if I could create the illusion of motion. I started with a single pixel random walk. It's a bit choppy, but you do get the sense of it moving around. Eventually, this evolved into a snake. Could this become a playable snake game one day? Maybe that's a project for the future. What else could we do with this? If you have ideas, I'd love to hear them. You could argue that it's more than a display. It has logic. It has memory. It's a soft robot. I'd love to scale this up even further, but before that, there are still a few kinks to work out. And if you want to follow this project, consider subscribing. See you in the next one, and stay soft.